Share screen. And I'm going to start up here. All right. Welcome, scholars. Welcome, YouTube. Let me see. So we are at the top of week, what is this, week 6, right? So hopefully you all had a good weekend. You were able to, do a little bit of what you wanted to do, mix with what you needed to do, and you got a nice balance, let me see. So the rhythm that we have going, for the remainder of the semester is basically we have 3 weeks of lecture and then a week of exam-related material. 3 weeks of lecture, exam-related material. So with this being week 6, you can anticipate exam 2 to occur during week 8. You just want to be sure that not only are you doing our assignments that are on Blackboard or the Pearson stuff, but we're also completing our lab with Dr. Lamar, right? So hopefully you've connected with her and you're basically following her instructions. When it comes to the midterm and the final, she's going to give me a grade for each student that I'm going to incorporate into each of you all's grade, and it counts for whatever she gives me. I'm going to scale it so that it's 10% of your overall grade. This is remote asynchronous. You're not obligated to stay. Let me see. But we are here, and I usually I try to just make myself available during the time. And I just go through the lecture and the homework just to fill the air. But if you guys wanted to work through like homework, we can. We don't have to do the stuff that I'm doing. Again, I'm just doing that just to come with some material, so we're not sitting in dead air. I can't think of anything else. We talked about the lab and the homework, yeah. So, well, we're just continuing where we left off. So I think we've been working our way through chapter 1. I think we're gonna touch on a total of 6 sections in chapter 1. So this is section 1.5, transformations of functions. Last time we talked about 1.4, a library of basic functions. And so now we're going to take those basic functions like we had y equals c, which was like y equals some number, which is a constant function. So that was like a flat line, or we had y equals x, which is a diagonal line. X squared was a parabola or a U-shaped curve. X cubed was an S-shaped curve. Square root of x was the top half of a sideways parabola. Absolute value of x was a V. And there are a few others, right? So we did what we could together. I would encourage you to, check out my pre-recorded lectures because I go through the entire section. Whatever, when we're together, we only have like 50 minutes. So I'll go through what I can for the 50 minutes. But in those pre-recorded lectures, I go through pretty much all the details from each section that's available in the slides. So then what we're going to be doing today is taking those basic functions and now extending it and doing manipulations on those functions to start to generate graphs, right? So section 1.5, transformations of functions. Some objectives are we like to define transformations of graphs, use vertical or horizontal shift to graph functions, use reflections to graph functions, and use stretching or compressing to graph functions. Okay. So transformations, if a new function is formed by performing certain operations on the given function f, then the graph of the new function is called a transformation of the graph of f. So let f of x equal absolute value of x. That's going to be our basic function. And then we're going to consider g of x, which is our basic function plus 2. And h of x is our basic function minus 3. We're asked to sketch the graph of these functions on the same coordinate plane and describe how the graphs of g and h relate to the graph of f. Okay. So hopefully you have a sense of what's the generic shape for absolute value of x, right? So absolute value of x makes the shape of a V, right? Where the V is at the vertex is at the origin. And then we're going to see what happens to that V when we add 2 on the outside of our basic function or subtract 3 on the outside of our basic function. So what we're going to do is basically make a table, choose several values for x, find the corresponding f, g, and h, and then plot these 3 graphs or these 3 functions on the same coordinate plane. So make a table of values and graph the equations. Let me see if I do like this. Does that fix it? Nope. Like this. OPM. Okay. So first we chose several values of x. So absolute value of x is the positive distance a number is away from 0. So for instance, the absolute value of -5 is 5, absolute value of -3 is 3, absolute value of -1 is 1, so on and so on. So absolute value is the positive distances a number is away from 0. So then for the second function, we're adding 2 on the outside of our basic function. So that's basically like saying adding 2 to all our y values. The x values stay the same, but we're adding 2 to all the y values. So on and so on, right? So then we see that when we added 2 on the outside, it took our original graph and shifted it up 2 units. So adding a 2 on the outside, we're like adding 2 to all the y values, shifted the graph up by 2 units. So similarly, subtracting a 3 on the outside of our basic function caused our original graph to go down by 3 units. Okay. So hopefully this is okay. This section is like, it's not difficult, but it is a little bit tedious. And oftentimes students experience like information overload, right? It's like the concepts aren't difficult to grasp, but all strung together in this fashion, it's kind of like information overload, right? And the only way you kind of get comfortable with that is just through repetition. So just practice and doing it over and over and over, and eventually it sinks in. It sinks in and it becomes second nature. Sorry about that. Mouth was getting dry, so I ate some grapes. Oh my goodness, it's so delicious. So to kind of recap. So if we consider some positive number, when we add a positive on the outside, it takes our basic function and shifts it c units up. If we subtract a positive number on the outside, it takes our basic function and shifts it c units down. So we add a positive on the outside, the original graph goes up. We subtract a positive on the outside, the original graph goes down. As usual, if anything is not clear, feel free to unmute yourself to get my attention, right? So we saw what outside manipulations adding and subtracting did. Let's see what happens when we do inside manipulations, adding and subtracting. So we're going to start with the basic function of y equals x squared. And then we're going to subtract 2 on the inside of our basic function and add 3 on the inside of our basic function. And just like in the previous example, we're going to basically make a table of values and plot the points and compare the graphs. So we just chose several values for x, and then we pass them through our basic function, and then also pass them through where we subtracted 2 on the inside. All right. So the first result we got was 36 and then 25. And then notice that the results started repeating two terms down. And then on the right-hand side, we had something similar happen, but it started repeating three terms up, right? But they're all repeats. Okay. So then if we plot all of these ordered pairs on the same graph, the blue is our original, which is y equals x squared, right? Notice that when we subtracted a positive on the inside, your intuition might say, oh, you're subtracting, so maybe you're going the negative x direction, but in reality, it's the reverse, okay? So the thing here, inside manipulations typically cause a horizontal change, and they typically are the reverse of our intuition. A negative, subtracting a 2 on the inside, move the original graph in a positive x direction. Adding a positive on the inside, move the original graph in the negative x direction. The way I kind of remember it, I asked myself, what value of x makes this 0? Or in other words, what's the x-intercept there? Well, positive 2 is the x-intercept, so that means we went to the right by 2. Negative 3 is the x-intercept there, so we went left by 3. So yeah, Inside typically is the reverse of our intuition. Let me just check the chat really quickly. Chat looks good. I already lost. It should be 6. I think we lost 2 people. Let's keep going. Okay. All 3 functions are squaring functions. G is obtained by replacing x with x minus 2, right? And so the x-intercept of G is 2. In other words, 2 makes G 0. So for each x comma y on our basic function, there's going to be a corresponding point x plus 2 comma y on the graph of G. Right? So it's a little bit funky on the inside interior, but you know, it's just basically the reverse of our intuition. When we added 3 on the inside, the x-intercept was -3. Guess I can close this because we only got like 5 people in this class, which is awesome. Shut that down. Shut this down. Okay. Okay. So then for horizontal shifts, let me see. So say we consider some positive number. When we subtract the positive on the inside, it causes a horizontal change and it should go to the right, C units to the right. When we add a positive on the inside, the basic function is going to be shifted C units to the left. Okay. So I think we've talked about 4 of the 10 transformations. Add a positive on the outside, it goes up. Subtract a positive on the outside, it goes down. Add a positive on the inside, it goes to the left. Subtract a positive on the inside, it goes to the right. Okay. So those are the 4 that we have so far. So this one asks us to sketch the graph of the function, and we can use transformations, right? This is basically like a sentence or a story. This is describing to us the shape. So the way you translate it, this says that the original graph is the top half of a sideways parabola. So we're starting with the square root function, which looks like the top half of a sideways parabola. Then, so when we're doing multiple transformation in one graph, the recommendation is to work our way from the inside to the out. So then the innermost transformation is we're adding 2 on the inside. All right, so that should cause a horizontal change and it should be the reverse of our intuition. So this is basically saying start with the top half of a sideways parabola that starts at the origin. This says to go left 2 units and then to go down 3. Do that one more time. Square root is our basic function. It says, that's saying start with the top half of a sideways parabola. This says to go left 2 units. This says to go down 3 units. So you see the basic function. Now what they did, they rewrote it into this form. Because notice we had +2 and -3, and they got a -c and a +d. So that +2 they rewrote as minus a -2. That -3 they rewrote as plus a -3. So then in this form, we see that our c is -2 and our d is -3. So that c being -2 tells us to go, that's like basically because -2 makes the inside part 0. So that says basically we went left 2 and down 3, which is the same thing that we said. Oh, it's not there anymore. Okay. So you see it here. Here's the original square root of x, top half of a sideways parabola. Notice we went left 2 and then down 3. To get the final graph, right? So that's all we did. These are called rigid transformations. We're just moving it, sliding it left and right and up and down. Okay. So we've discussed, 4 transformations? So now it's time for the next set of 2. So the first of the 2 is reflections in the x-axis. So the graph of y equals negative times f of x is a reflection of the graph of our basic function in the x-axis. So with this negative being on the outside, it's like our y values are going from positive y to negative y. So it's flipping vertically, it's flipping top to bottom. It still follows what we said before, where outside manipulations cause a vertical change and it flips it top to bottom. If a point x comma y is on the graph of our basic function, then the point x comma negative y is on the graph of y equals negative 10 seconds. Because again, it's like our y's are going from positive y to negative y. Okay. So notice the x values are staying the same, but the y went from positive y to negative y. Multiply the outside by a negative. So outside manipulations, like they seem like they're only affecting the y value. All right, so that's why it's causing vertical changes. Inside manipulations are only affecting the x value. So that's why it's causing horizontal changes. Okay. So we talked about flipping over the x-axis. Now we want to see reflecting in the y-axis. So now instead of multiplying the outside by a negative, now we want to consider multiplying the inside by a negative. This is going to be a reflection of the graph of our basic function over the y-axis. So it's going to flip horizontally. And see, that follows what we said before, inside manipulation causing a horizontal change, right? If a point x comma y is on the graph of our basic function, then the point negative x comma y is on the graph of f of negative x, right? Notice the y values stay the same, but the x's went from positive x to negative x. So that caused it to flip horizontally. So like in this, all right? The y's stay the same, but then x went from positive x to negative x. Okay. So explain how the graph of this guy here, can be obtained from the graph of absolute value of x. Okay, let me just check something really quickly. I'll be right back. Okay, that's good. So, give me just a moment. Okay. Okay. So our basic function is the absolute value of x, right? So absolute value of x, we said is basically a v where the vertex is at the origin. And then when we do multiple transformations in one go, the recommendation is to work your way from the inside to the out. So the innermost manipulation is going to be this -2, where we subtract 2 on the inside. So we know it's going to cause it to move 2. Now, that should be a horizontal change. Your intuition might say it goes to the left, but it actually goes to the right by 2 because 2 is the 0 there. So we want to go 2. We want to go right 2 units. Okay. So this says go right 2 units. So the next manipulation to consider is this negative on the outside of our basic function. Outside manipulations only affect the y, so it's going to cause a vertical change and tends to follow our intuition. So if our y is going from positive to negative, then that's going to cause it to flip vertically. Flip over the x-axis. Okay. And then that +3 tells us to go up 3 units. Okay, so absolute value of x is basically the v, and we're following the vertex at the origin. This guy says to go right by 2. This guy says to flip over the x-axis, and this one says to go up by 3. Okay. V V, we said go right 2, flipped vertically, and then go up by 3. This time it's 420. Now it's 421. So we started with the absolute value where the vertex is at the origin. We went right by 2. And then we flipped vertically. So flipped it top to bottom because of the negative. And then we went up by 3. All right. Right 2, we flipped, and then went up 3. Okay. And if, the reason we suggest working your way from the inside to the out, because it does seem like the order is important and it can affect the way the final graph looks. Like if you do it the wrong order, sometimes it does throw the graph off, right? I think the order is important. So in this example, we're given the f of x is the absolute value of x, so that's our basic function. Now we're multiplying the outside by a number larger than 1. And we're also going to consider we multiply the outside by a number between 0 and 1. And we want to see how these manipulations affect the graph. So, we're going to choose several values of x, which is already done for us, and then pass them through these 3 functions, okay? So absolute value of x, that means this is going to be a 2, 1, 0, 1, 2. G is 2 times that, so it's like our y values get multiplied by 2. So then this is going to be a 4, 2, 0, 2, 4, okay? And then for h, our y values are cut in half. So half of 2 is 1, then a half, then 0, 1/2, and then 1. And we're going to plot these ordered pairs on the same plane. You get something like this. So absolute value of x is our original, that's the v, okay? When we multiply the outside by a number larger than 1, the red is what we call a vertical stretch, right? So it still causes, outside manipulation still causes a vertical change, and it still follows our intuition. We multiply the outside by a number larger than 1, then we got a vertical stretch. When we multiply the outside by a number between 0 and 1, it causes a vertical shrink or compression towards the x-axis, okay? Notice the x values stay the same, but the y values are either being multiplied by a factor of 2 or a half. Okay. So the graph of 2 times absolute value of x is the graph of the basic function vertically stretched by multiplying each of the y coordinates by 2. And then it's 1/2 times the absolute value of x is our basic function vertically compressed by multiplying each of the y coordinates by a half. Okay. And this one. So then for vertical stretching or compressing, the graph of y equals a times f of x is obtained from the graph of our basic function by multiplying the y coordinate of each point by a and leaving the x coordinate unchanged. And then the result is we get a vertical stretch away from the x-axis if we multiply the outside by a number larger than 1. We get a vertical compression towards the x-axis if we multiply the outside by a number between 0 and 1. So we still get our vertical changes, and it follows our intuition. If a is negative, then we just graph the absolute value of a times f. We just basically do the same thing that we did previous, but then we take that result and flip it over the x-axis. Okay, because it's like the y goes from positive to negative. Thank you. Oh, it's a typo. Anyway, so horizontal stretching or compressing. So in the previous slide, we looked at multiplying the outside by numbers either larger than 1 or between 0 and 1. Now we want to look at multiplying the inside. If we multiply the inside by a number between 0 and 1, that follows the reverse of our intuition and causes a horizontal stretch. If we multiply the inside by a number larger than 1, it follows the reverse of our intuition and causes a horizontal compression towards the y-axis. And then it's a similar argument if b is negative. Okay, let me kind of just check the Zoom really quickly. Check. That looks okay. Okay. So using the graph of a function y equals f of x in a figure whose equation is not given, sketch each of the following graphs. Okay, so we just have this is just a generic figure, and then some generic figure f of x. So then we want to see what happens when we multiply the inside by a half, the inside by 2, and the inside by -2. So multiplying the inside by a half is gonna cause a horizontal change. You might be tempted to say it causes a horizontal compression, but remember the inside manipulations are the reverse of our intuition. So this actually causes a horizontal stretch by a factor of 2 units away from the y-axis. So this first one is going to cause it to stretch horizontally. The second one is going to cause a horizontal compression by a factor of a half. So you're going to multiply each x. They're basically going to be cut in half. All right. So it's going to cause a horizontal shrink towards the y-axis. And then this last one is going to have the same result, but now if we multiply the inside by a negative, it's going to cause it to flip horizontally over the y-axis. So we said horizontal stretch, horizontal compression, and then take that result and then flip it over the y-axis. Let's see. So stretch the graph horizontally by a factor of 2. So in our new function, for each x and y that we have in the original, our new function is going to be 2x comma y. Okay. So then this one, compress horizontally by a factor of a half. For every x comma y that we have in the original, our new one is going to have half of x comma y. Okay. And then the last thing we said was it's going to be the same result, but then we flip it horizontally over the y-axis. And you see it here. Okay, so that it takes practice. I feel like the concepts are not difficult. I feel like they're simple. It's just not easy in the sense that it can be information overload. It's like a lot of like random information all at once that you have to manage, right? And so to me, that's the real challenge. Well, I guess we did almost finish in one of my classes. We can talk about this one. So we're actually sketch the graph of this function. Can anybody identify the basic function here? It's the function that we're considering. All right. So our basic function, we're going to start with x squared, which is a parabola, right? And so then when we go to do our manipulations, we want to work our way from the inside to the out. So the innermost manipulation is where we subtracted 1 on the inside. So that should cause the new graph to go to the right by 1. So we're going to take x squared, we're going to go right 1 unit. 1 unit. Oh, I'm totally sleepy. I'm trying to honor you guys' time. We have a solid 15 minutes. We'll see where we finish. We'll see how we feel. And once we get to the same spot we got to with the others. So the innermost transformation, this guy, sorry. All right. So this -1 had us go to the right 1 unit. don't know what that is. Working our way from the inside to the out. Next, we're going to consider this 2. I know it's -2, but we're going to just look at the 2 for right now. So we multiplied the outside of our basic function by 2. That's like multiplying the y values by 2. So then that's going to cause a vertical stretch by a factor of 2. So vertical stretch by a factor of 2. Next, we multiply the outside by a negative. So that's like the y's are going from positive y to negative y. So then that means we're going to flip over the x-axis. And then the final one, we added 3 outside. So that's like adding 3 to all the y values. So that's going to cause the graph to go up by 3 units. Okay. So start with the U-shaped curve, go right 1, stretch vertically by a factor of 2, flip vertically, and then go up 3. Okay. So we start with a U-shaped curve with the vertex at the parabola, at the origin. We went right 1, stretch vertically by a factor of 2. So the x value stayed the same, but the y values got multiplied by 2. And then we reflected about the x-axis. And then I think we said go up by 3. You get an image like this, all right? Well, we're essentially there. Let's go ahead and finish this out. Because I made it here with the group from before, but let's go ahead and finish it out. Oh, it's this one. No, this is where we stopped. We can take a look at it. I'm probably going to rely on my notes. Let's see. So for an artery wall with a radius r, the velocity v of the blood flow at a distance r from the center of the artery is given by this model here, where c is a constant that is determined for a particular artery. We write v equals v of r. So the velocity based on the radius is given by this guy here. Starting with the graph of y equals r squared, sketch the graph of the new function, given that the artery has a radius 3 and the constant is 10 to the 4, right? Let's just plug that in really quickly. Okay. So then we want to consider v of r. It says that the radius is 3 and our c is 10 to the 4. So we're going to have 10 to the 4 times 3 squared minus r squared. Okay. So it says starting with r squared, right? So r squared would be a parabola, a U-shaped curve. Let me think about it. I think we need to rewrite this, and we need to rewrite it in the following form. The 10 to the 4 is fine. But I think we need to factor out the negative. So I'm going to rewrite the inside as a negative r squared minus 9. Okay. I feel like that helps us to keep track of like the signs and how everything works. Let's just try this and see what happens, right? So I took the information that they gave us and plugged it in, but I rewrote it. When I plugged it in directly, it gave us this, but then I rewrote it and it gave us this, right? And I was intentionally just put it in this form. So now if we work our way from the inside to the out, this says we're starting with a U-shaped curve. Hopefully this works. This says to go right by 9, right? So we have a U-shaped curve. We went right by 9. Then we flip. Let me think about it. If we go right 9, if we flip horizontally over the y-axis, does that put us at -9, right? Let me think about it. Oh, you know what might make it easier? Will that help us? It might help us to take that negative and move it to the outside. Hmm. Let me think. Let's keep going. So U-shaped curve, we go right 9. Now, if we flip over to y, that should put us at -9. Let me see, if we left it at +9, yeah, we're flipping over the y, right? I'm gonna go with it. So now we're at -9, and then we stretch it vertically by a factor of 1,000, 10,000. Let me see something. Still something I'm not convinced in before, because I'm just trying to get a sense before I look at the result. An artery with a radius r, velocity of blood at a flow distance r from the center of the artery is given by this, right? Because like when I think about it, I'm just kind of playing around with stuff in my mind, right? So like if we start here with a U-shaped curve, that -9 tells us to go to the right 9 units. So say we're like over here. But then when we flip horizontally, I'm just going to delete this. It looks like it's putting us here, right? And I don't know, I'm not vibing with that. Because then when you stretch it vertically, you're still going to get something like this. Artery with a radius r. Only other thing, there's one other thing I'm thinking about doing now is basically passing this negative to this guy, because you can move it further out, right? So then what would happen there is that we would stay here, but then it would flip vertically. Okay, let's just look at it. I was just trying to get a sense without looking at the result. Let's look at it because we have it. But I like the second thing that I said. Let's see what they did in the notes. Okay, so if we compare, we started here, right? And I think we got this. Oh, okay. I guess that could have worked. I didn't even think about that. They went on and distributed this guy. They just simplified it, right? And they got something like this. So then this would say, if we kind of ignore all this for right now, this says start with what? A U-shaped curve. You stretch it vertically by a factor of 1,000. You flip it vertically. And then that's what I was looking for. You move it up by like 90,000. That's what I was looking for. I was like, why is this not behaving properly? So but you see the difference, right? I was like, I knew I was anticipating something like this, right? I was looking for that. And whatever we had, we were over here, right? And I was like, that's not working. Something's not right there. The thing was, I think we should have expanded it further, right? For this example. So we got to this and we were fine, but then they went on and distributed this guy. All right. So then now when you look at it from here, we're starting with a U-shaped curve, stretch vertically by a factor of 10,000, flip vertically, and then move it up by 90,000. And then after those transformations, now you get this guy that you see here, right? So then, so if the radius of the artery was what, 3 units? So then the little r was the distance away from the center of the artery. So think about it. The further away you get from the center of the artery, the lower the blood flow. The closer to the center of the artery, the higher the blood flow. That makes sense, right? This result makes sense. Okay, but that was interesting, right? Lesson learned. So with this one, we should have, and I'm gonna just do this in another color. The main thing here, I'm gonna X through this. It's not really wrong, but it's missing the point. We should have distributed this guy. And then when we did that, it would have been in a form that then we can apply the transformation. Right? That one would have gotten it for us. Okay. And then you see it here. So first you start with r squared. And then this says to stretch vertically by a factor of 10,000. And then that negative right here has us reflect over the x-axis and then go up 90,000 units. And then this is our graph. Okay. So then we get the velocity of blood decreases from the center of the radius. So when the radius is 0, we have the highest blood flow. And then when we're at the artery wall, we have the lowest blood flow, where it ceases to flow. The portions of the graph corresponding to the negative values of R do not have any physical significance, right? So if we're talking about artery blood flow, everything that was negative, we just ignored it, right? Okay, and I think that brings us to the end. So you guys were the only ones that made it to the end of this section together, all right? That's why I kind of stumbled a little bit on that last one, but that's okay. Okay. Are there any questions? Did you guys want to ask any questions? Okay. Let me go ahead and load a copy of this so that you can pull it up. So you can access the PDF from any of our sessions from now to the beginning of the semester. Also, you can access any PDF from any of my other College Algebra courses as well. Okay. I can't think of anything else. So if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Stay dangerous and peace.